Hello. Once again, we pursue our study of integration. And today we shall devote one whole lesson to the fundamental theorem of calculus. Why? Because in our view, it was the one, and it is known, that it is the theorem really which had brought a revolutionary concept to the science of calculus. So, and if the student will have one day to memorize anything about his studies of mathematics, so in my view, it is this particular theorem that he will memorize. Why? Because it is the theorem that he shall be using all the time to carry on integration. Of course, we had to introduce the notion of Riemann integral because there we established the exact notion of integration, whereas it's the fundamental theorem of calculus that the student will usually regularly use. So, as I said, we should go into detail and explain the theory much further. Now, this theorem, in this lesson, we shall be speaking about the first fundamental theorem, and the first fundamental theorem is the one which leads to the second theorem. Now, this theorem usually is not mentioned in books of calculus, but it deserves to be also exposed. Next, we shall be focusing on the second fundamental theorem, and finally on improper integrals. And improper integrals, it's Cauchy in the late 18th century who had, or beginning 19th century, who have introduced these improper integrals. Because the fundamental theorem constitute a method to calculate integrals, but for continuous function over closed bounded domain. So we have to introduce another notion called the improper integrals. Now, about the first fundamental theorem, we shall be talking about now, is that this theorem says the following. Now, if f, and this we have to note in great detail to clarify how really such a theorem leads to the notion of integration of continuous functions. Now, if f is integrable in a, b, now here f is integrable, it's not necessarily continuous, just integrable, then the function capital F of a of x, which maps x into the integral of from a to x of f of t dt for all x element in a interval I, is continuous. And that's the first theorem called the first fundamental theorem. So if f is integrable, it means that capital F of a is continuous. Now, the second, it has actually two results. Well, the second result of the first fundamental theorem, it says that whereas if f is also continuous, small f is continuous, then capital F of a is differentiable, and the derivative of which is equal to small f of x. Now, to prove the first one, when small f is integrable, then capital F is continuous, is easy. It has to rely on that the small function, that the small f is bounded, because integrability of f on a closed interval ab, we said before, if f is bounded on a closed interval, then it is integrable, or it has a finite number of discontinuity. Then it's integrable. So from this result, or from this postulate of integrability of f, one can easily extract the notion of, or the result that capital F is continuous. Whereas if small f is continuous, then we can show easily that capital F is differentiable. And to do this, we do the following. Now, here we have f of a, which maps x into the integral from a to x of f of t dt. And if we want to calculate f dash of x, what we do is that we take the limit 1h tends to 0. This we do in our lesson of differentiation. Here we have capital F of a of x plus h minus capital F a of x divided by h. And this here, since small f is a continuous function of t, and since f is integrable, and we said before that capital F is continuous, and therefore we take the limit here for h tends to 0 of the integral. We substitute for capital F of a of x plus h from a to x plus h of small f of t dt minus the integral from a to x of f of t dt. And then here what we do is that they take the limits Of course, this is divided by h, so we divide here by h, and we take, so you have here you divide here by h and take the limit when h tends to 0. Now we apply here some properties of definite integrals. We said that when you have the integral from a to x, we can substitute this from x to a, because the integral from a to x is equal to negative the integral from x to a. So you have here the negative from x to a plus the integral from a to x plus h. So what you end up with from x to x plus h of f of t dt. Now this integral here, we saw before that this integral here, using what's called the mean integral theorem, the one that we had in our last lesson, we said that if small f is continuous, then the integral from a to b is equal to f of zeta. This is equal to here again 1 of h. This is equal to f of zeta times b minus a, which is here x plus h minus h, which is h. This cancels out, and you have f dash of zeta. So when you take the limit, of course, zeta here lies between a and x and x plus h. So actually, when you have h tends to 0, you have also zeta tends to x, because zeta lies between x and x plus h. So when h tends to 0, zeta tends to x, and you had at the very end you have here, I'm sorry, this is not f prime, this is f of zeta, and you have here f of x. So what we have actually proved is we have proved that the derivative of capital F dash of a of x is equal to small f of x, which means that the function capital F of a of x is the antiderivative of small f, or we can say that any continuous function f, and this is the result we should reach, that if you have a continuous function, a small f of x, then small f, then if small f is continuous, then it has at least one antiderivative. And the antiderivative, you can express it in this form, and this is the form you already dealt with when we spoke about continuity of functions and how this represents area between the point A and the point X. Now, so the first fundamental theorem, it tells you again that if small f is integrable, capital F is continuous, whereas if small f is continuous, then capital F is differentiable, and the derivative of which is equal to small f of x. Now you can, for example, take this example. This function, it's not continuous, and therefore you cannot apply the fundamental theorem, yet it is integrable. Why? It's integrable because it's bounded, and it is continuous except at finite number of discontinuities. Here you have only one point of discontinuity at the point x equal to 0, and therefore this function is integrable. And because it's integrable, according to the first fundamental theorem, capital F of a of x must be continuous. So if you integrate this function over any closed interval containing the point x equal to 0, you obtain here f minus 1 of x. In other words, you start from the point minus 1, and you integrate this to obtain minus 1 plus mod x, and minus 1 plus mod x, this is a continuous function for all values of x greater than equal to minus 1. Why? Because f was already integrable. Now again, here you apply the first fundamental theorem. The second result, this function is the composite function of two continuous functions from 2 to x. Therefore, this square root of 1 plus t squared is continuous, and therefore, since it's continuous, then this integral is a differentiable function of t. You can differentiate it to obtain the function itself, which is square root of 1 plus x squared, and here it is. Now we come to the second fundamental theorem. Now the second fundamental theorem is the following. It tells you, and this is a result of the first one, it tells you that if f is continuous on the closed interval ab, then the integral from a to x is equal to capital F of x minus capital F of a. In other words, you can use an antiderivative of small f to obtain the area in the interval from a to x. Now, of course, if this theorem here, it tells you that this is a necessary and sufficient. In other words, necessity is easy. You can differentiate this to obtain the derivative of f prime, which is a small f of x. But at the same time, you can also, if you can say the following. You have here f of a of x, which is equal to the integral from a to x to f of t dt. Now, since you know that this is an antiderivative of as we said last time, from a to x of f of t dt, then it must be equal to any other antiderivative of the same function, small f plus a small constant. Because we know very well that antiderivatives, they differ by constant. And this we said it in our first lesson of integration, when we consider the indefinite integral. We said that if you have two indefinite integrals of the same function, then they must differ by constant. And since this is an antiderivative, and this represents an antiderivative because f of t is continuous, then you have here another antiderivative, capital F of x plus c. But then to obtain c, what you do, as we did in the last lesson, is that you can substitute x for a. This cancels out, and this becomes capital F of a, and c becomes, this is equal to, since c plus f of a, capital F of a is equal to 0, so you get c minus f of a, and you end up with what? Then the integral from a to x of f of t dt is equal to capital F of x minus capital F of a. In other words, this is the second fundamental theorem, and it tells you directly, if small f is continuous, then the area under the graph y is equal to f of x in the interval from a to x is equal to the antiderivative of f minus at x minus the antiderivative at the point a. Now, of course, usually books, they write it in this way. They put here a b, and substitute x for b, and you get the same thing. In other words, you have to define here your integral over the interval from a to b. It doesn't matter whether from a to b or from a to x. And this here is the result that you obtain, that the integral of a continuous function, small f over the interval ab is equal to capital F of b minus capital F of a. In other words, you calculate the antiderivative, and the antiderivative exists from the first fundamental theorem. Since the function small f is continuous, and therefore capital F is differentiable, and since capital F, which is the integral from a to x of f of t dt, represent an antiderivative, in which case, because the derivative of which is equal to small f of s, so actually here what you do is that you take an antiderivative and you subtract two antiderivatives, one from a at the point a and one at the point b. And here it is, you apply your second fundamental theorem. For example, here the function, it's a continuous function. Because from the point minus 1 here, it's from minus 4 over 3, which you fear to have a root in the denominator. But from the point minus 1 to 3, this function, because the domain of this function is the open interval from minus 4 to 3, so here this function is continuous because square root of a continuous function is continuous, the composite function again. So because it's continuous, therefore on the interval, the closed interval from minus 1 to 3, you can apply the fundamental theorem. What you do is that you calculate one antiderivative, and here is the antiderivative of this square root, because all you have to do is just differentiate it, and you will find out that the derivative is equal to this. So what you do is that in order to calculate your integral, what you do is that you calculate the value of this function, which is the antiderivative of the function small f of x here. You first substitute the point 3 to calculate this expression here, and you subtract from it the value at x is equal to minus 1, and here it is. This is the value of your integral. Again, this is a modulus of x minus 1. Again, you can, of course, find an antiderivative of this particular expression here, while you can simplify this by doing a certain substitution, because the method of substitution allows you, instead of having an integral over x, an integral or on another, using another variable. So what we shall do here is that we shall substitute for x minus 1 is equal to y. So what you get here, from here you get the x, using the Leibniz differential, you get the x is equal to dy, and here we substitute mod x minus 1 is equal to mod y, and then you have to watch out for the limits of integration. Now the limits of integration concerns now the new variable y and not the old variable x. So since y is equal to x minus 1, then when y is equal to minus 1, what's the value of x? It's equal to 0. When x is equal to minus 1, y is equal to minus 1 is equal to minus 2. So you start from minus 2. And when x is equal to 2, you substitute x is equal to 2, you get y is equal to 1. So now your integral, again, mod x minus 1 is a continuous function. You can apply the fundamental theorem, but instead of carrying out the integral on x, you carry it in on y. Now you have to search to look for an antiderivative of mod y, but with this we can look it up either in the book, or you can find it as half y mod y, because once you differentiate this, you got y, and this is easy. The derivative of y mod y with respect to y is equal to the derivative of the first one times mod y plus the first one times the derivative of mod y we saw before divided by y, so you get twice mod y. So the derivative of of this expression here, it's equal to mod y, and then what you do is that this is the antiderivative of this function here. All you have to do is you substitute first at 1 and you subtract from it the value of at -2 and you get 5/2. Again, evaluate the integral of ln mod x. Now ln mod x here, this we have seen in the lesson of integration by parts. The only way of doing this integral is integration by part, and yet from -2 to -1, and we said before that this is a function which is, this function here looks like this. It's a function which is, the domain is R except 0. You want to carry on the integral from what? From -2 till -1. In other words, you want to find out this, the area here. So what you do is that you do it by integration by parts. Integration by parts allows you, and you remember the lesson, we said that the easiest way to put the introduction 1 times ln x, and you integrate 1 to obtain x. The other one without change. And there is no point to stay till the end to substitute for your limits of integration. You can directly substitute from 2 to -1 minus the integral, again, the integral of 1, which is x, times the derivative of ln mod x, and we saw this before. The derivative of ln mod x is the same as the derivative of ln x, except that one is defined for x greater than 0, and the other one, ln mod x, is defined for all x except x equal 0. And here it cancels out to obtain here this expression. All you have to do is that you substitute with the limit integration, and you get this result here. Now, sometimes you have, you remember in the lesson of integration by part, we said to deal with square roots, the best thing is to do some transformation. So the best transformation in this case, you substitute x is equal to sine theta or cosine, doesn't matter. Now here again, instead of carrying out the integration, and then at the very end, you substitute for x, and then you substitute for the limit of integration of x, the best thing, and once you leave x to another variable called theta, then you have to carry on the integral in terms of theta, and you substitute for the limit of theta. Now, what are the limits of theta? Since you substitute x is equal to sine theta, then when x is equal to 0, theta is equal to 0. Whereas when x is equal to 1, what's the value of theta for which sine theta is equal to 1? Is pi/2. So the integral now, instead of being for all values of x from 0 to 1, is the closed interval from 0 to pi/2 with respect to theta. And this is easier. And then there is no point of going back again to x. So here again, what you do is that the square root of 1 minus sine square theta, which is cosine square theta. Under the square root, it's cosine theta. But then the x is equal again to cosine theta theta. So you have here cosine square. And the only way to carry out the integral of cosine square is to substitute for double the angle. And once you do you substitute for cosine square is equal to half plus half cosine twice theta, then you carry out the integral here of cosine 2 theta, which is half sine 2 theta. And here again, you substitute for the limit of integrals, and you get pi/4. And again, actually, you may not be using all these steps because you know this well. This is the equation of a circle, and this is from 0 to 1. This is 1/4 of the circle with radius 1. What can you expect about the area of a quarter of a circle is equal to, since the area of the circle is pi, so this quarter of a circle becomes equal to pi/4. But this is a simple exercise to show you that there is no point of when you do a certain substitution, then you leave the original variables and you go ahead with your new variables. Now here is an interesting function, because this function here is defined by two rules. One for x less than 1 and greater than or equal to half, and the other one is more than 1. How do you carry these kind of integration? You have two options. One of them is to carry on the integration from 0.5 to 1, and this is the way actually it's easier for the students. You do the integral for the first rule from 1/2 from 0.5 to 1, and then for the second rule you carry on the integral from 1 to 2. Here is the first method. You integral from half to 1 plus the integral from 1 to 2 separately, and you get the result of integration. But what is interesting here, this is why I want to show this integral, especially this particular function, because this particular function, yet it is defined by two rules. It is continuous. So according to the first fundamental theorem, it tells you if the function is continuous, then the integral from a to x is a differentiable function, and therefore it has an anti. In other words, capital F of a is an antiderivative. So if you have a continuous function, then surely it must somehow has an antiderivative. So what is an antiderivative of function given by two rules? Does it exist? Yes, it does. And actually, I have been trying there is no one sole antiderivative, but I was able to calculate an antiderivative of this particular function. This function has two rules, and yet since it is continuous at the point 1, therefore it must have an antiderivative according to the fundamental theorem. So I've been searching for an antiderivative, and I found this one. All you have to do, you apply the second fundamental theorem. You substitute at the value x is equal to 2 minus the value of f at half, and you get the same results. Again, you may have, for example, a function given in terms of two rules, but the function may not be continuous. So how can you deal around this sort of function? Like, for example, this one. This function is integrable. Why is it integrable? Because it is continuous except at one point of discontinuity, and therefore it is integrable according to Riemann, because it's defined on a closed interval. So how can you do this? What you do is that here you cannot find an antiderivative because the function may not have an antiderivative because it's not continuous. And yet, since it is integrable, what you do is that you can calculate the integral from 0 to 1 and from 1 to 2. Now, from 1 to 2, the function is defined at the point 1. So you can say that here you can apply the fundamental theorem directly because the function is continuous on a closed interval. But here the problem is here. Here at the point 1, this rule is not defined at 1. What can you do about this one? Since you know that it's integrable, all you have to do is that to assign it a value here equal to the limit of this rule from when x tends to 1 from the left-hand side. In other words, you can give it a value here equal to the limit of this rule here from the left-hand side. In other words, you take the limit of the function from the left-hand side when x tends to 1 from the left-hand side, and this limit you can assign it to the value of the function at the point equal to 1. In which case, then this rule here, or the value of the function here, f of x here, becomes continuous in the closed interval from 0 to 1, and therefore you can apply the fundamental theorem. Here is it. It's the rule from the right-hand side is continuous, so it goes automatically to apply the fundamental theorem, whereas on the left-hand side, it becomes equal to 1 plus x when it is less than 1, whereas at the point x equal to 1, all you have to do to give it the value of the limit of this 1 plus x here when x tends to x from the left-hand side. Now here the function now becomes continuous on the closed interval from 0 to 1, and then here only that you can apply the fundamental theorem, and you carry on the integral once from 0 to 1 on the first rule, and 1 from 1 to 2, and this is here the result of your integration. So still there is no obstacle, and still you can apply the second fundamental theorem. Now, for function of this sort, cosine x squared, some teachers say, for example, this kind of function we cannot integrate. We cannot integrate cosine x squared. We cannot integrate e to the power x squared because we could not tell what is the antiderivative of such functions. It's not true, because and yet we cannot obtain a set of elementary functions to represent the antiderivative of such functions, but the antiderivative exists. Why the antiderivative exists? Because this function is the composite function of two continuous functions, and therefore it's continuous, and from the first fundamental theorem, since the function is continuous, then it must possess at least one antiderivative. And the way of doing it, we cannot integrate it by the usual way. What we can do is that you can use Maclaurin expansion, and this we've seen in the lesson of Maclaurin and Taylor. You expand the function in the form of a power series. Here, the cosine t is equal to 1 minus cosine x, 1 minus x squared divided by the factorial 2 plus x to the power 4 divided by the factorial of 4. What you do is that you can replace x by t squared, and you get this series, which is a Maclaurin series, and it's convergent for all values of t. What you do is that you integrate it term by term, and here is your series, which in fact is not very beautiful, but yet it is an antiderivative of your original function. Now, about improper integral. We've seen before that we spoke about the fundamental theorem, and we said that the fundamental theorem, in order to be applied, you apply usually either to functions which have an antiderivative or mainly to continuous functions. But usually the fundamental theorem is applied on a continuous domain, and not only that, but even the Riemann integral, the function is bounded on a closed interval. In other words, you seek to determine the different integral on a continuous function or on bounded functions over a closed interval. But if the function is unbounded or it is defined on an open interval, in this way, in other words, an unbounded closed sort of domain of intervals, then you may not apply the theorems that we have exposed. The theorem which we have exposed concern functions that are either continuous or bounded on a closed interval. But if the function is not bounded or not defined on a closed and bounded interval, for example, from 1 to 2, from minus pi by 2 to pi by 2, this sort of closed bounded interval, then there is this person, this mathematician called Cauchy. He has so many contributions. He introduced the notion of improper integrals by which he can transform his integral, since the idea is to find a limit of some form of like the Riemann sum, for example, some form of series, and this form of sum, if you take the limit and exists, then the integral exists. If this is the idea, then we seek to transform this kind of integral in which the function is not bounded, or in which the interval itself is not closed and bounded, to a form amenable which you can apply the theorems that we have just explained. So these kind of improper integrals, as I said, they either integrals defined on a sort of unbounded intervals, or in their integrals in which the integrand itself, it means the function that you integrate, is unbounded over the integral of interval of integration. So these two situations, you have to transform the integral, and this is what is called improper. In other words, ill-defined. In other words, not amenable to apply the theorems that we have just explained. So what you do is that you transform them. For example, this one here, 1 over x squared, and you wish to integrate from 1 to infinity. Now you have the interval of integration is from 1 to infinity. You cannot apply the theorems that you have just mentioned before. So what we do, it's easy. Cauchy had the idea that we define f over a closed interval from 1 to c. And then here the function becomes continuous. So you apply, for example, the fundamental theorem, and then you take the limit when c tends to infinity, and you reach the same results. So for example here, we want to integrate 1 over x squared from 1 to infinity. So what we do is that instead of infinity, you put c. Now here, since c is a definite value, so this 1 over x squared now becomes continuous over closed bounded interval, so you can apply directly the fundamental theorem, and it is continuous. So what the integral of 1 over x squared is equal to a minus 1 over x. You substitute from 1 to c, you got 1 minus 1 over c. But already you want the integral from 1 to infinity. It's easy. All you have to do is that you take the limit from when c tends to infinity. So this cancels out, and you obtain 1. So while students usually, I accept from them that to carry on the integral just like that, and to say that this vanished out, etc. But from the proper point of view of integration, we have to be more precise. I mean, mathematicians like to be more precise, because here a function is not it's not defined of a closed bounded interval. So what you do, it's a trick that Cauchy has to proceed with in order to transform your integral into the integral in which you can apply the fundamental theorem. So while 1 over x squared, what you do, instead of 1 from infinity, you get here 1 over c first, to be more precise, and then you take the limit when c tends to infinity to obtain the integral, to calculate the integral which you started with, and here you obtain 1, and we call this integral a convergent integral because it leads to a value. Now 1 over x from 1 to infinity, you do the same thing. You take the limit when c tends to infinity, and you evaluate the integral over the closed bounded interval from 1 to c. 1 over x gives you ln x. But ln x, when you substitute, you got ln c minus ln 1, which is 0. But ln c, when you take the limit when c tends to infinity, you get infinity. In other words, this integral is not, we call it not convergent or divergent. Calculate this integral. Now, this integral here, you remember the lesson on partial fractions. What we do is that, first of all, it's from 0 to infinity. So there is no fear. Why? Because here the denominator, here the domain of this function is what? R, except what? Minus 1, and minus 2, and minus 3. But we integrate from 0 to infinity. So there is no fear here to stuck with one of the roots of the denominator. But to integrate such function from 0 to infinity on this an unbounded closed interval, so what you do, you substitute instead of infinity c, and then you take the limit when c tends to infinity. Now, how can you carry on this integral? You have to find set of partial fractions to replace this whole rational function. And to obtain it, it's very easy. We said before, we shall here try to do it through the method of the residues. What you do is that you multiply in order to obtain, for example, we put it in the form a1 divided by x plus 1 plus a2 divided by x plus 2 plus a3 plus x plus 3. Suppose you want the value of a1. What you do, you multiply this rational function here by x plus 1, and you take the limit when x tends to minus 1. So when you multiply by x plus 1, you end up with what? 1 over x plus 2 times x plus 3. You put x is equal to minus 1, so this becomes 1. And this becomes 2, so you have 1 over 2, and here it is. So a1 is equal to 1 over 2. Suppose we want a2. You multiply by x plus 2, and you put x is equal to minus 2 in the product of 1x plus 1 times x plus 3. When x is equal to minus 2, you have here minus 1, and you have here what? You have here 1. So you get minus 1. So in other words, you have here 1 divide minus 1. So a1 is equal to minus 1, etc. And then you carry on the integral. The integral of the first one is equal to what? Is equal to half ln x plus 1. And this one, again, it's half ln x plus 3. So you add them together. Ln plus ln, you get ln of the product. And since you have half of ln, it means ln of the square root. Minus the logarithm of x plus 2. So you divide by x plus 2, and this is the end result. Now what you do, you have to substitute. You have here the ln of square root x plus 1 times x plus 3 divided by x plus 2. You substitute c is equal to 0 to equal to c first. So you have this ln value here, minus the value at x equal to 0. So when, when x equal to 0. So when x equals 0, you get here what? You get the value of ln. This is 0, so it is 1 times 3 under the square root divided by 2. Now you take the limit only when c tends to infinity. When c tends to infinity, what you get? The ln of the square root here, what you get c, you remember the horizontal asymptotes. When you take the limit when c tends to infinity, here you introduce the limit under the ln sign, and you take the limit of this expression here. Now the limit here, you take c square outside, and you end up with what? Mod c divided by c. And the rest becomes equal to 0. And then you take the limit 1 mod c over c, which is what? C is positive. So you get what? You get 1. So, and ln 1 is equal to 0. So this cancels out, and you end up with minus ln square root of 3 divided by 2. This is a very nice, actually, example here. Here again, the integral from minus infinity to infinity. Here you have two, you want to integrate over r. So what we do, we have to divide the integral into two integrals. One, for example, from minus infinity to 0, and the other one from 0 to infinity. Now, the first one, which is from minus infinity to 0, all you have to do is you substitute for minus infinity is equal to c1, and then you take the limit when c1 tends to minus infinity, whereas for the second one, you can substitute for infinity c2, and then you take the limit when c2 tends to infinity. Here you have one. Here you have an integral which is defined on a closed bounded domain, and the same on a closed, on a closed bounded interval from c1 to 0, and the same thing here, so that you can carry out then both integrals using the fundamental theorem. Now 1 over 1 plus x squared is no more than the arc tan 10 minus 1 of x. You substitute for 10 minus 1 0, which is 0, and you left out with minus 10 minus 1 c1, whereas the second one, the same thing, is 10 minus 1 c2 minus 10 minus 1 0, which is 0. And then after that, you take the limit when c tends to minus infinity, and we know that 10 minus 1x is a function which is what? Which has domain R, and the range is what? Is minus pi by 2 to pi by 2. So when you take the limit when c1 tends to minus infinity, this you obtain minus 10 by 2, and you have here minus, so minus of minus 10 of pi by 2, you get pi by 2, whereas 10 minus 1 c2, actually it's worth to draw it. Here is like this. This is the 10 minus 1 function. It ranges from minus pi by 2 to pi by 2. So when you take the limit when x or c tends to minus infinity, you get minus pi by 2. Whereas when you take the limit when x tends to infinity, you get pi by 2. So finally, what you have here, we have the result is pi. They add them up to obtain pi. Now sometimes you have an improper integral, and you don't wish to know the value of the integral. You just want to know whether it exists or not. So there are some theorems for that. These are tests. For example, you have two functions, two continuous functions, and defined of the closed interval from a to infinity, and they are under some kind of improper integrals. So it tells you, there is a theorem which tells you For example, if f is smaller than j and j is integrable, as in improper integral which exists, which converges, then f also converges. So here, this is the theorem. If g of x is convergent, then f of x is. Whereas if f of x is divergent, then g of x is. And these resemble very much the theorems that we have exposed when we spoke about series. You have one which is convergent, is bigger than the other one, so the other one is convergent. While when this is greater than this one and this diverges, the other one diverges. And actually, we can apply it on very simple example of this one. Here, for example, we have 1 over the square root of 1 plus x cubed is less than 1 over x cubed. Whereas 1 over x over the power 3 over 2 from 1 to infinity, you can check that it's converged. All you have to do to carry out the integral here, and you take the limit and you integrate using the fundamental theorem from 1 to c, you find equal to 2. So this integral converges, whereas the function here is less than this one, of course. So since this one converges, the other one also converges. Here it is. According to the theorem, this one converges, as we found out, and this is less than, the function here is less than this one, so this function must also, the integral here must also be convergent. Now, the other type of integral, when the function is unbounded, for example, 1 over square root of x, in the limit, when you take the limit when x tends to 0 from the right-hand side, you find equal to infinity. How can you carry this sort of integral? The same thing exactly. What you do is that instead of defining the integral from 0 to 1, you define it from c to 1. Now, from c to 1, now, the function is defined on a closed bound interval. You carry out the integral here, and then you take the limit finally when c tends to 0 from the right-hand side. Here again, this is the integral from c to 1, and then you get 2 minus 1 square root of c. Now, if you want the integral of this function in which the function is unbounded in the neighborhood of 0, what you do is that here you take the limit when c tends to 0 from the right-hand side. So here you start by an integral which is improper integral. The function is unbounded in the neighborhood of 0. You substitute from 0 to c. You calculate the integral using the fundamental theorem, and then you take the limit when c tends to 0 from the right-hand side, and you find to be convergent, and the value is equal to 2. For example, here, this is a function which is a sine function here. Where is the problem? The problem is that at the point 1. It's improper because at the point 1, this goes to infinity. So what you do is that you carry on the integral, you substitute instead of from 0 to 1, you take it from 0 to c. Now from z, since it's from 0 to c, the function is bounded over this interval. You carry out the integral. This is one of the elementary functions, and you know that the antiderivative is directly sine minus 1c. And then later on, at the very end, what you do is that you take the limit where c tends to 1 from the left-hand side, and we know that this is a function or which the range vary from minus pi by 2, so it's equal, the value is equal to pi by 2. So we came up to the end of the lesson, and it's very important to have exposed this fundamental theorem, because the fundamental theorem, as I said before, it is the theorem that the student will be always using it all the time. I mean, during your study in economics, what you shall do when you carry on integration, you evaluate integration defined on a closed bounded intervals, and in which the function is continuous. So it's worth exposing this theorem. And as I said, if you remember anything of your study in mathematics, you remember always the theorem that in order to calculate integrals of continuous function, all you have to do, search for an antiderivative, and you can look it up in your book, or you can memorize it, or you can try by yourself doing it using the method of integration, that substitution, whatever, integration by parts, all these methods that you have exposed. Once you obtain antiderivative, you substitute between, you subtract the value of f between, which is capital F, the antiderivative between the two limits of integration, and here you have evaluated your integral. At the end of this important lesson, I wish to thank you for your attention, and remind you again that all these lessons are uploaded to the site of the Union Telematic University. And until we meet again, I thank you for your attention, and I wish you a very good luck.